Welcome to this explainer. When you watch a chemical reaction happen, it's easy to think it's just pure magic, right? But today, we're pulling back the curtain. It turns out chemistry isn't some chaotic magic show at all. It is actually a strict, incredibly elegant system of biological and physical accounting. Every single atom is tracked. By the end of this, we are going to become molecular accountants, mastering the absolute art of stoichiometry and balancing chemical equations.
Here's our roadmap for today. We've got 6 stops: the magic versus the math, the ultimate law, translating chemistry, balancing rules, a masterclass, and finally, adding context. Basically, we're taking a journey from the foundational laws of mass straight into a hands-on masterclass where we'll balance some pretty complex equations together.
All right, let's jump right in. Section 1, the magic versus the math. Like we said, we usually know a reaction happened because of stuff that looks a lot like magic. Crazy temperature shifts, wild color changes, or new phases of matter just appearing out of nowhere.
Let's start with a classic mystery. Imagine you take a chunk of pure sodium and drop it into a flask of chlorine gas. It is a violent, completely chaotic interaction. Sparks, heat, light, the whole shebang. So, what is the actual result of this intense clash between these two highly reactive elements?
Well, the crazy thing about all that violence is the entirely mundane result. All that heat and light, that's literally just physical accounting at work. The atoms are rearranging themselves to form plain old, harmless table salt, a white solid of sodium chloride. Nothing new was magically created out of thin air. The atoms simply found a new, stable arrangement. Which brings us to Section 2, the ultimate law, mass conservation. Because to really understand how these atoms rearrange themselves so perfectly, we need to establish the ultimate rule of our chemical ledger.
First up, we gotta understand our environment. In an open system, stuff can freely enter and leave. Think of a hot cup of coffee just letting steam drift off into the room. But to track our chemical accounting properly, we can't have runaway atoms. We rely on a closed system, like a tightly sealed flask. Nothing gets in, nothing gets out. Period.
And that beautifully illustrates the golden rule for this explainer, the law of conservation of mass. Inside that closed system, the total mass absolutely does not change during a chemical reaction. Matter isn't popping into existence or vanishing, it's just shifting around in our accounting book. If you start with exactly 10 grams of reactants, you are absolutely going to end up with exactly 10 grams of products. No exceptions.
So how do we actually track this mass mathematically? That brings us to Section 3, translating chemistry, formula equations. We have to translate our real-world observations into written chemical equations.
Back in the day, we might have used word equations, literally writing out sodium plus chlorine yields sodium chloride. But hey, we're chemical accountants now. We need precision. So we're moving away from describing reactions with words and translating everything into formula equations. We're using chemical symbols to represent exactly what's going on, like taking the word sodium and turning it into the symbol Na.
Now here's the absolute game changer for balancing these symbols: coefficients. These are the big numbers we place right in front of the chemical species. They tell us the number of molecules involved. So if you slap a big 2 in front of that Na, that coefficient tells you that you've got 2 completely separate sodium atoms. Notice we aren't changing the molecule itself, just how many of them we have in the ledger. This is our primary tool for stoichiometry, balancing the ledger and making sure the exact number of atoms going in matches what comes out.
All right, Section 4, Balancing Act, the rules. Balancing equations is famously a trial and error process. It's kind of like a giant Sudoku puzzle, but our source material lays out a few crucial suggestions to guide us.
First and foremost, and this is a big one, only use coefficients. Never, ever change the tiny numbers inside the chemical formulas themselves. If you change H2O to H2O2, you literally just turn drinking water into toxic hydrogen peroxide. Bad idea. Second rule, try to balance your metal atoms first, since they usually dictate the reaction. Third, treat a blank coefficient as a 0. Well, actually, scratch that. A molecule without a number in front obviously means you have at least one of them. But from a pure accounting mindset, treat a blank space as a 0 in terms of what you've actively added to the balance so far. And finally, save your tricky diatomic elements, stuff like O2 or H2, for the very end, because they are way easier to scale as a grand finale.
Okay, let's put these rules to the absolute test. Welcome to Section 5, the Masterclass, Complex Balancing. We're going to dive into a detailed stoichiometry explanation and balance a highly complex organic reaction together.
Just look at this absolute monster of an equation, C19H17NO3 plus O2. This is a massive organic molecule combusting with oxygen. Carbons, hydrogens, and oxygens are scattered everywhere. But hey, don't panic. We are going to tackle this ledger systematically, one element at a time.
All right, following our rules, we scan for metals first. There aren't any. So, we start with carbon. We have 19 carbon atoms locked inside that giant molecule on the left, which means we need exactly 19 CO2 molecules on the right. Simple enough. Next up, nitrogen. We only have one single nitrogen atom on the left, but look at the right. It naturally forms a diatomic pair, N2. To temporarily balance one atom against two, we use a sneaky mathematical placeholder, a coefficient of 1/2, right in front of the N2.
Now, obviously, we can't leave half a molecule floating around in our final accounting, so to clear that fraction, we just multiply the entire equation by 2. That one starting molecule, it becomes 2. Our 19 CO2s, they double to 38. And that half N2 becomes a nice clean 1. Let's tackle hydrogen next. Our newly doubled molecule on the left now gives us 34 total hydrogens, because 17 times 2 is 34. To match that on the right, we drop a 17 in front of the H2O. Finally, the grand finale, oxygen. Let's tally the right side first. 38 CO2s give us 76 oxygens, plus 17 from our water. That's a whopping 93 oxygen atoms. On the left, our main molecule already gives us 6, right? Because 2 times 3 is 6? So we need exactly 87 more from our diatomic O2. We use another temporary fraction, 87 over 2, and multiply the whole shebang by 2 one last time to clear it. That progressive, step-by-step scaling, that is the true heart of stoichiometry.
Wow. Okay, now that the math is flawlessly balanced, we've got to add the real-world physical context back into our equations. Let's hit section 6, adding context, phases, and types.
A chemical equation doesn't just tell us how many, it also needs to tell us what state. We do this by adding little lowercase letters in parentheses. S for solid, L for liquid, G for gas. Oh, and AQ is a super important one, aqueous, which just means the substance is dissolved in water. Also, as we definitely saw in our masterclass, we always have to remember that 7 specific elements are naturally diatomic. They just love to pair up in nature, like O2 and N2.
Beyond just the physical phases, we can also categorize our balanced ledgers into main types of reactions. Starting with synthesis. This one is super straightforward. Simple ingredients joined together to form a much more complex product. A plus B yields AB. Think of carbon and oxygen combining to form carbon dioxide.
Then we have the exact opposite, decomposition. This is a reaction where a larger, complex compound is broken down into its basic elemental parts. So AB simply breaks apart into A plus B.
And finally, we have combustion. This is exactly what we just conquered in our masterclass example. A hydrocarbon, a carbon-based molecule, burns in the presence of oxygen. The really amazing thing about combustion accounting is how totally predictable it is. No matter how massively complex the starting hydrocarbon is, the products on the other side of the ledger are always exactly the same: carbon dioxide, water, and a big release of heat and light.
Now, that actually brings us to the very bottom of our ledger. Once you truly grasp the chemical reactions are just this strict, elegant mathematical accounting, man, the whole world just looks different. You start seeing this hidden ledger balancing itself everywhere. So, I'll leave you with this. Look around your room right now. What unseen, perfectly balanced chemical equations are happening right this second? In the flame of a candle, or the slow rusting of a nail? The math is always balancing, whether we bother to write it down or not. Thanks for joining me on this explainer, and keep looking for those equations hiding in plain sight.